All right, welcome back, class. This is Lecture 3 of Chem 220A. I want to begin by reflecting on some of the lessons we learned in the previous lecture and what we've built up to this point. So the most important thing that we have stated thus far is our fundamental postulate, from the statement from which everything else is being derived. That statement, hopefully you all remember, is a statement about the probability of observing a microstate in a very particular kind of system, that which is isolated. We've expressed it in the following way: for fixed energy and set of mechanical variables, things like volume and number of particles, that is what constitutes our isolated system. The probability of a microstate is a constant. Another way of saying that is all microstates are equally likely. Mathematically, we denote probability with little p, microstate with little nu, in a fixed energy and mechanical variable system. That probability is a constant, and we've given that constant a particular name. We've called it omega, which itself is a function of those things that we fixed, typically energy, volume, and number of particles. Where this omega just counts up the number of microstates consistent with those constraints. Just normalizes that probability. For a large system, that omega is an incredibly large number. In fact, we worked out a general expectation for how that omega, how the number of microstates scales with the extent of the system. We found that we should generally expect that omega, dependent on extensive variables like energy, volume, and number of particles, should go like some little omega, which is a function of intensive variables, things like the energy density, epsilon, or the mass density, molecule density, number density. Something that is independent of scale to the n. That is to say that the number of microstates grows exponentially with the size of the system. So if I double the size of the system, the number of microstates will be squaring the number that I originally had. If n is Avogadro's number, this is an enormously large and unfathomably large number of microstates. We gave this specific form, this exponential form, where I have pulled out the scale of the system into that exponent, something called a large deviation form. And it is it is the expected dependence, which we argued by noting that it is the dependence we would find provided we're able to break up a large system into independent regions. The fact that the number of microstates grows so large, and consequently that fluctuations for large systems appear to be suppressed, is essentially a mathematical way of reconciling the paradox that we confronted in the first lecture, that while we know that the world is made up of atoms and molecules, macroscopically things look boring. This is that explanation for why things look boring, because the numbers that dictate probabilities grow so large that only their means dominate. Last lecture, we hit upon a fairly profound statement. We uncovered a simple deductive reasoning for a law that you were probably taught long ago as children. The second law of thermodynamics tells you the direction of spontaneous processes. It uses complicated concepts like notions of entropy and it increasing. Given this microscopic underpinning that we're developing, we have a very simple way of understanding what the second law is in terms of probability. In fact, we formulated a probabilistic statement of the second law. At log of omega, the number of ways something can happen increases in a spontaneous process for an isolated system. In a fixed energy and mechanical variable system, an isolated system, because all states are equally likely, the most likely thing to have happen is just the thing that can have the most ways of occurring. If omega enumerates the ways in which something can happen, that means that improbable states become more probable, or states with fewer numbers of ways of happening will spontaneously evolve to states with more ways of happening. So an abstract notion like the second law is reduced to nothing more complicated than a statement of probability that I think you all have intuition for. If I flip 10 coins and get all heads, that's a very improbable event. More likely than not, if I flip another 10 coins, I'll have something which is much more probable, something which has many more ways of happening, namely that I'll more likely than not have 5 heads and 5 tails. Now, if I'm only flipping 10 coins, the probability that I get 10 heads, though small, is not infinitesimally small. If I flip an Avogadro's number of coins, I can, with high likelihood, expect to have nearly 50% heads and tails. So this probabilistic understanding of the second law led Boltzmann to a definition of what the entropy means microscopically. S, standing for entropy, has units from those silly thermodynamicists. Those units are now written in terms of Boltzmann's constants, KB. And Boltzmann told us that the entropy microscopically is nothing more than that constant times log of the number of microstates. If the number of microstates, number of ways something can happen, denotes the direction of spontaneous change, well, he reasoned then that that must be microscopically what we mean by the entropy, at least for a fixed system. This KB is nothing more than a more sensible rewriting of the ideal gas constant, put in terms of molecules. And if we were to assign a numerical value to it, it's a number which is very small in units that are common to us living on macroscopic scales. So things like joules per Kelvin. It's something which is order 1 in a per molecule basis, or a per mole basis. So something incredibly small on a per molecule basis. So again, this was Boltzmann's definition of the entropy, just relating it to the number of microstates. Okay, so that's the review. We've stated our fundamental postulate. We have some expectations for how states grow with increasing system sizes. From this, we've deduced the second law, and following that with a definition of what we must mean by the entropy. All right, so I want to do 2 things in this lecture. I want to revisit the derivation we did last lecture, acknowledging that most systems aren't in fact isolated. Typically, at very least, they're able to exchange energy with their surroundings. We've already noted the consequences of that in terms of how it changes the probability of microstates. So I want to redo that derivation because it gives us a form for the probability of microstates which is easier to use. I want to then talk a little bit more about the definition of temperature that becomes invoked as we do that derivation. We've rationalized that that definition obeys some of the properties we would expect, namely that defining the temperature as how the number of microstates change with energy yields statements like that if I put something in a system in contact with a bath at one temperature, it will come to that temperature at equilibrium. That's what we proved last lecture. We can actually say a little bit more about the direction of spontaneous change and the direction of spontaneous energy change, given this definition of temperature and our statement of the second law, and we'll explore that too. And we'll end today with a generalization of this procedure for those cases like Aditya brought up in our last live session. What happens if we open the system up and let not only the energy change, but mechanical variables as well? Okay, so let's start by, again, acknowledging that most systems are not isolated. And developing some intuition for what happens for a system in contact with a bath that it can exchange energy with. So we constructed this setup from our isolated system, our rigid, impermeable, and insulated box. Within which, because everything inside that box is isolated, we know the likelihood of observing any configuration of the total state of that box. Inside it, we carve out what we want to define as our system. Everything else is therefore what we denote as a bath. And we envisioned the case where the two can exchange energy. All right, so everything inside the box in there has fixed energy. So there is some total energy. I'll denote ET, which is fixed. And it can be written as a sum of the energy of the system, which depends on the microstate of the system, plus the energy of the surrounding bath, which depends on what microstate it is in. The microstate of the system, denoted nu, and the microstate of the bath will denote nu sub b. So the combined system plus bath is isolated. So we know that the probability of observing a microstate, which we need to specify both in the system and in the bath, is just a constant, which depends on the total energy that I've constrained. But for a specific state of the system, if I set nu, there is, in principle, many possible bath states which will satisfy that constraint. We only require that if I look at the bath, that the energy associated with that state is equal to the fixed total energy less that the energy of the system in the state that I've set. So concretely, I could imagine the system in a state where all of the particles in that system are over on the left-hand side. There are many possible arrangements then of where the particles in the bath are, consistent with a restriction that their energy plus the energy of that specific state of the system sum to the total fixed energy. A little more concretely, the probability of observing just the system in some specific state, therefore, is equal to the probability the system was in that state and the bath was in some state, say nu B1, some specific arrangement of the bath consistent with our total energy constraint, plus the probability that the system was in state nu and the bath was in some other state, still consistent with that total energy, etc. So the total probability of the system being in a specific state is the sum over the probabilities of the system being in that state and the bath being in any number of states. Because this combined system, the combined box, which is specified state of the box, which is the system plus the bath, is itself an isolated system, all of these probabilities are equally likely, so they're all just a constant. So the probability of the system, therefore, just depends on how many terms are in that sum. Something will denote omega b. the number of bath states consistent with the energy of that system state. We can enforce that consistency by noting that the energy of the bath needs to be equal to the total energy less that energy of the system. Now, we are free to construct this world as we see fit. So we will take a case where the system is really small and the bath that it is embedded in is really large, such that if energies are extensive, that component to the total energy, due to just the system, is small. If it is a small contribution to the total energy, while we don't naively know the form of omega b, we can get some insight into its functional dependence on the energy of the system by performing a Taylor expansion. So again, we did this last time, but I just want to go back over it, expanding that form to first order. We have that log omega b is equal to log omega b at the total fixed energy less the energy of the system times how the number of states in the bath change with its energy. Plus higher order terms, but that expansion is rapidly convergent if the bath is really large. This derivative, how the number of states in the bath changes with its energy, is what we've defined as beta, which is nothing more than the inverse temperature written in units of Boltzmann's constant. So putting the realization that the probability of the system being in some state is just proportional to the number of bath states, with the now functional form, or the functional dependence on the number of bath states on the system energy, we find what is known as the Boltzmann distribution, that the probability of observing the system in some specific state is proportional to the exponential of minus beta, the energy of that state. That's the so-called Boltzmann distribution. It says that while our postulate says in an isolated system, if energy is fixed, all states are equally likely, if I open that system up and I do the counting, such that I acknowledge that the system and bath have to be in specific sorts of states so that the energy of the universe is conserved, the probability of observing just the reduced state, just the information in the system, now generates an exponential dependence on its energy. And provided beta is greater than 0, we find that there is an apparent bias towards lower energy states. The probability of observing a state is exponentially suppressed in its energy. Okay, so this is a bit abstract. Let's see how it works in a concrete, simple example that we can essentially solve for exactly. Let's consider a simple two-level system. So we can illustrate that two-level system it's a system which can exist either in some state, let's call it state G for a ground state, with energy that will set as our zero of energy, or in some higher energy state, we'll call E for excited, that has some corresponding energy greater than zero, we'll denote as epsilon. Now, from our Boltzmann distribution, we can immediately answer questions like, what is the relative probability of seeing the system in the excited state as compared to the probability of seeing it in its ground state? Now, we have only worked out a proportionality for the Boltzmann distribution, how the state of the system depends exponentially on its energy with some constant of proportionality, but that constant is just that. It's just a constant. It is independent of the state. So if I take a ratio, P of E over P of G, that constant will drop out. It's maybe worth noting that in a two-level system, the state of the system, what nu is, just labels whether the state is in that ground state or in the excited state. So in fact, the microstate is uniquely defined by just one number or one subscript, G or E. Using the Boltzmann distribution, I find that that ratio is a ratio of exponentials. E to the minus beta epsilon is the energy of the excited state. E to the minus beta 0 is the energy of the ground state, which then can be simplified as that ratio yielding just e to the minus beta of that epsilon. So indeed, provided epsilon positive and beta is positive, the relative likelihood of finding the system in its excited state is exponentially suppressed with epsilon, with its energy. We can work out a couple limits to get some more intuition. As beta goes to infinity, which is the same as temperature going to 0, because beta is 1 over temperature. If beta goes to infinity, e to the minus infinity is just 0. So as we go to really low temperature, it is increasingly unlikely to find the system in the excited state relative to finding it in its ground state. Alternatively, as beta goes to 0, the temperature is like going to infinity. Well, what's the relative probability now? E to the minus beta, or e to the minus 0, what number is that? That number is just 1, which is kind of interesting. At infinite temperature, this result says that I don't favor going to high energy, which some of you might have expected, but rather the ratio, the relative likelihoods of being excited or being in the ground state are equal. So at high temperature, I don't favor high energy. I just make those states equally likely. In fact, if I was to plot this, so the probability of seeing the system in its excited state as a function of temperature. So we've got the limits worked out. It starts at 0. It will go to, if the ratio is 1, that means the absolute probability of being in the excited state at high temperature does not go to 1, but goes to 1/2. If both states are equally likely, then the probability of one of those states is just 1 over the total number of states. In this case, just 2. So the probability of the excited state as a function of temperature will have this sort of sigmoidal form, where that crossover depends on that characteristic energy scale, epsilon, in units of beta. Again, the surprising result is that at high temperature, it's not that the Boltzmann distribution tells us we should expect high energy states to be more probable. It just makes those states as probable as other states. So it's not that we get a bias towards high energy as we increase the temperature. Rather, we just reduce the preference for low energy states. And the relative scale to compare temperature to are the relative energy gaps, the energy differences between states. So it's worth thinking through what sorts of scales will allow for specific sorts of excitations, or how big is KBT compared to typical excitations we might think about in molecular systems. If I need Kb, Boltzmann's constant, times temperature to be on the order of an energy gap in the system for there to be appreciable likelihood for an excitation to exist, it's worth knowing how to formulate KBT, an energy unit, in terms of characteristic excitation energies. So, maybe we can discuss in our live session on Thursday what the size of KBT is for typical molecular excitations, things like vibrations, rotations, and translations. All right. Now, from our definition, that T inverse is how the entropy changes with energy at fixed mechanical variables, which is nothing but, in units of Boltzmann's constant, how the number of states changes with energy. We know that the temperature is typically positive. So the left-hand side of that equation is positive, which means that there must be, in general, many more states at higher energies. So the fact that this is positive means that the number of states increases with energy. So that actually explains our intuition for why we typically think that energy increases with temperature, or increases with temperature, because as we increase the temperature, it's not that we are promoting states to be at higher energy or making them more probable than being at low energy. It's just that there are so many typically states at higher energies relative to lower energies that the multiplicity, the degeneracy, the number of ways that the system can be at higher energy means that that average is going to be dominated by those more vastly occurring high energy states. We'll come back to that notion in a second, the idea that typically there are more states at higher energy. You might think to yourself, are there counterexamples of this? Are there cases where I increase the energy and actually find smaller numbers of states? Through this definition, that would imply that the temperature goes negative. Can that happen? Mind you, this temperature is a thermodynamic temperature. It's an absolute temperature. So I'm not talking about trivial reasons why you might have a negative temperature, like having -5 centigrade. I mean, is it possible to have -5 Kelvin? Is that possible? What do you think? Before we go there, we should really try to convince ourselves that this definition of temperature is actually reasonable. So let's continue thinking through it. Let's go back to isolated systems to do that. All right, let's draw our little isolated system. You all now know what that looks like. It's our box wrapped in insulation. It has fixed energy and some set of mechanical variables. Now within that box, I can imagine distributing the energy and those mechanical variables in a number of different ways. Another way of saying distributed or placed, they could be partitioned in different ways. For example, let's be fancy. Let's copy that, paste it over here. Ooh, I can even align it. Look at that. All right. Let's, for example, imagine a partitioning enforced by some constraint where I have energy E1 on the left-hand side, energy E2 on the right, correspondingly mechanical variables x1 on the left and x2 on the right. That is a partitioning I could imagine establishing in the system. Now, if I have some energy and some mechanical variables in each one of those partitions, I could take in that information and I could count the number of microstates consistent with that fixed energy and mechanical variables. Might not be a very pleasant thing to do. If those numbers are large, counting might take a while, but in principle, provided I know the fixed E1 and X1, I could go in and do that counting. Now, if I can count the variables consistent with E1 and X1, that means I know omega for that constraint, which means that I know the entropy by just taking the logarithm and multiplying by Boltzmann's constant. Now for fixed total energy, which is given by sum of E1 and E2, and fixed total mechanical variables, the volumes and numbers of particles, we have a notion of what sorts of changes will be spontaneous. A spontaneous change how the system would repartition itself must increase the entropy. Now that's total S, so the change in the entropy under those isolated system constraints will be positive. It is zero only at equilibrium. The number of states is maximized at equilibrium. Equilibrium is the state of the system which is most probable, which is the state that I see, given I leave the system alone. So we have all the ingredients now to be able to ask about what happens in those spontaneous processes. We know how to compute the entropy. We know how the entropy is therefore related to things like energies and mechanical variables. We know that it's just the number of ways things can happen is what increases the entropy, or what looks like apparent directionality increases in spontaneous changes. So let's do a thought experiment with this construction. Let's imagine taking an improbable state and asking to which probable state does it go to? Let's do this by imagining preparing a given partitioning of this isolated system where I have energy E1 on the left, energy E2 on the right, associated mechanical variables, and put a wall in such that that energy and mechanical variables initially can't exchange. Now, if I know the energy and I know the mechanical variables, we've just argued that I can compute the entropy. That's just counting the states consistent with those constraints. So this wall does not allow the energy or the mechanical variables to exchange. So I can go in, compute the total energy as a sum of S1 and S2. That will be some number. Now let's actually take that partitioning, take that little wall I've introduced to allow for no exchange to happen, and open it up such that the energy can change. Let's allow heat to flow. But let's not allow the volume to change or the number of particles to change. All right, so the mechanical variables by construction stay fixed, but the energy changes. So E1 will change by some amount delta E1. E2 will change by some amount delta E2. And correspondingly, there must be a change in entropy. Delta S1 and delta S2. So the total energy is fixed. So that means that any gain on the left must be offset by a loss on the right. Another way to say that is delta E1 and delta E2 can't be independent. They must be equal and opposite to each other. So let's just call that delta E. That's just conservation of energy. That's just an implication of a mechanical system, be it quantum mechanical or classical. Now we can actually ask questions about how large is that delta E and what is its corresponding sign. Specifically, our second law says that delta S has to be greater than or equal to 0. In improbable partitioning, should it change, we'll move to a more probable partitioning. Delta S can be written as a sum of delta S1 and delta S2. Now let's imagine that we didn't start so far away from equilibrium that we aren't so far away from the most probable arrangement of the system, and thus consider a case where delta E is small. That would mean that to first order in delta E, the change in the entropy for a system 1 is going to be delta E1 times how the entropy changes with energy. The entropy is a function of the energy in mechanical variables. If the energy changes by an amount delta E, if delta E is small, there will be a corresponding change in the entropy that goes like delta E times how the entropy changes with energy. Now, how the entropy changes with energy, well, that's what we meant by temperature, specifically 1 by temperature. That means that delta E, that the corresponding change in energy is delta E times the temperature of that system over on the left. I could similarly write down the change in the entropy of system 2. If system 1 gained some amount of energy, that means it was lost by system 2. And the corresponding change in the entropy will be that loss times 1 over its temperature. So putting together, the total change in the entropy is thus delta E is common. I can factor it out. 1 by T1 minus 1 by T2. And for a spontaneous change to have occurred, that needed to be greater than or equal to 0. So we now have a statement for what the sign of the energy is, dependent on what the difference in the temperatures were. If, for example, T1 were greater than T2, that would mean that 1 by T1 was less than 1 by T2. For a spontaneous change to have happened, it would mean, so T1 is less than T2, the term in the parentheses therefore is negative. It would have meant that delta E would itself have to be negative, such that the product is overall positive. That's a bunch of math language. What does that mean in words? Delta E is the heat, the energy flowing from one side to the other. It says that the heat flows. Delta E is negative. It went from system 1 to system 2. In this case, system 1 had a higher temperature. So heat flows from hot, higher temperatures, to cold. Completely consistent with our intuition. Heat flows from hot to cold because the temperature is essentially a measure for the potential for heat to flow. If I reversed it, the system over on the right, system 2, were hotter, energy would have flowed in the opposite direction. If the temperatures are equivalent, then there is no potential for heat to flow. No spontaneous change would occur that would change the energy. Such phenomena like heat flow are therefore said to be irreversible. In that the reverse doesn't happen. For a spontaneous process, heat flows from hot to cold, we don't expect spontaneously for heat to flow in the opposite direction, from cold to hot. That's to be contrasted with a reversible process, which has no net change in entropy. Okay, so I think, at some level, this should be all straightforward. It should make intuitive sense. Heat flows from hot to cold. That's old news. Now let's think back about what you know. You actually know that the world is made out of atoms and molecules. Atoms and molecules don't know about the second law. They just evolve with their relevant dynamical equations of motion. How do they know for heat to not flow from hot to cold? We've said that probabilistically, the second law is just a probabilistic statement about how improbable things likely become more probable things. We also know that macroscopically probability concentrates so that we only see typical behavior. So it's straightforward, I think, to buy into all of this, that at least macroscopically, these sorts of statements about irreversible processes, the fact that heat flows in only one direction, are true. But what if the system were smaller? What if we thought about heat flows in really small systems? Does it have to be the case that heat flows from hot to cold? If probability isn't concentrated such that there is some chance of seeing atypical behavior, to see fluctuations away from the mean, could we observe heat flowing in the opposite direction from what the second law would predict? Does that violate the second law? You should all think about that. Kind of fun things to ponder. Another question that we can address fairly simply is, since we've defined the entropy via Boltzmann is related to the number of states, and we've defined the temperature, at least its inverse, as how entropy changes with energy, fixed mechanical variables. Therefore, the temperature is nothing but how the number of states change with increasing energy. Does it have to be the case that the temperature is positive? This is a fun little game we can play. Let's actually ask that. Let's consider a system of two-level systems, what I like to call the wacky world of spins. So let's imagine we have n non-interacting systems. With energy levels like so. So I have energy increasing, going up. I have a ground state and an excited state. Spin number 1 can be in either its ground state or excited state. Spin number 2 independently could be in one of its two states. Let's say that it happens to be in its excited state. Can denote an arbitrary spin along this line with I. Maybe this ith one is in its excited state. And I will run up to n. Maybe the nth spin in this microstate is in its ground state. Each spin can either be in its ground state or its excited state. There are two possibilities. Now let's do some counting. So how many states have a given energy that we want to fix? So let's denote the total energy, ET. We can compute the energy of the system by just asking what energy level the ith spin is in, and then summing over all the spins. All right, so let's think about some concrete examples. If I set ET to be 0, how many microstates are there? How many ways can the system arrange itself such that it has 0 energy? The number of ways it can arrange itself we call omega. how many arrangements are there for ET equaling 0? Well, there's only one, right? For ET to be 0, it means that every single spin had to be in its ground state. If any one of them is excited, it will have an energy above its ground state energy. There's only one way. Similarly, if ET was in times epsilon, everything is in its excited state, there's analogously only one way for that to happen. All right, what about something in between? What if we ask for the total energy to be epsilon? Well, for a spin to have energy epsilon, it needs to be in its excited state. For the total system to have a total energy of epsilon, that means that only one particle can be excited, but any one of those particles could be excited, which means that there are n ways that that can happen. Now notice something interesting. If the system is in its ground state, in its lowest energy microstate, there's only one way for it to happen. If it's in its highest energy microstate, there's only one way for it to happen. But in between, there are more ways that it could happen, more than one way it can happen, which means that this function omega, as a function of its energy, has to be non-monotonic. In fact, if we were to plot log omega as a function of its energy, we would start at something low, go to something low, but in between have something like that, where its maximum is actually at n epsilon by 2. Those of you skilled with combinatorics could do the explicit binomial calculation, convince yourself that this is indeed true. This has a really interesting implication for what we mean by temperature. Temperature is how the number of microstates change with energy. If I look over on this side, d log omega dE is positive, like we intuitively expect the temperature to act. But on that side, the number of states as it changes with energy is negative. That's crazy. That means the temperature, the absolute temperature, the Kelvin temperature, can be negative. All right. We don't have a lot of common experience with negative temperatures, negative absolute temperatures. Why is that? What does negative temperature even mean? A way of asking that is negative temperature hotter than hot or colder than cold? All right, let's plot this again. Log omega versus E. So let's imagine partitioning our system. This is a closed system. The total energy is imagining to go through a sequence of fixed energy and fixed mechanical variables. Let's imagine fixing E1 and E2. Give myself a little more room here. Opening it up in a system of these spins. such that the energy can exchange between some of the spins and some other spins. And asking, just like we did before, how is heat going to flow if the system is made up of such a wacky arrangement such that the number of microstates actually is non-monotonic, actually has a maximum? Let's imagine E1 started over here. Its temperature, which is at that energy, how the number of microstates changes with energy locally, that derivative. The system over in E1 has a typical positive temperature. Let's imagine that the system over in E2 is over on this other side. It's prepared in such a state such that what we mean by its temperature is negative. The local derivative, how the numbers of states change with energy, is negative. So our second law calculation from before said that heat flows in the direction such that 1 over T1 minus 1 over T2 has to be greater than or equal to 0. Well, in this arrangement, T1 was positive. If T2 is negative, what does that mean? It means that delta E must be positive. So if I fix the total energy, I'm trying to go to a position that maximizes the number of ways something can happen, goes to a most probable state. The system over on the left will increase its energy. The system over on the right will decrease its energy, such that the system evolves to maximize omega. That means the system over on the left, E1, gained energy, or that heat flows from negative temperature to positive temperature. So negative temperatures are incredibly unstable. They will immediately lose energy even to a surroundings which itself is at very high, albeit positive, temperature. This is why we don't see negative temperatures without exerting a ton of effort. Anytime if we were able to create a negative temperature system, it would be so unstable, it'd lose energy so quickly and spontaneously, that it wouldn't last very long. Now, some of you, physical chemists listening to this lecture, have some direct experience with negative temperatures. Where do you actually observe negative temperatures in the laboratory? Yeah, that's right. In lasers, what you do with a laser is create so-called population inversion, where you excite more electrons to higher energy levels, so that you have more electrons at higher energy constantly radiating photons as they relax. But that requires a ton of energy inputted into the system to maintain. So even in a wacky instance like the spin system, our definitions of temperature seem to be consistent. All right, let's wrap up in the last 10 minutes or so by thinking about how we repartition mechanical variables. We've focused entirely so far on energy. Let's generalize our setup a little bit. Let's consider a vector of mechanical variables, which will pick out one to allow it to exchange, holding all the others fixed. All right, so our usual setup. We prepare the system over on the left with some energy, on the right with some other energy. We set a specific mechanical variable to be partitioned analogously. All the remaining will be held fixed. And if I have that specification, I know the energy, I know the mechanical variables, I can compute the entropy. Now let's allow, so initially block everything off, and allow heat or energy and that specific mechanical variable x to flow. So we can allow heat to flow by taking the insulation off that partition. We can allow x, say, the volume to flow by allowing that partition to move back and forth. Oh, I did something clever. Ha. All right, so we've punctured some holes in this partition, so the energy will have changed. That's old news. Needs to conserve energy. X1 will have changed. Now, the total system is isolated. Everything in the box has globally conserved quantities. So if X1 gains some delta X, that means that X2 needed to have lost it. This is physically intuitive if you imagine X actually being the volume. If the partition moved more to the right, that means that the volume on the right shrunk by the same amount that the volume on the left increased. We're fixing these other mechanical variables, the primes. And in general, there will be a corresponding change in the entropy due to this process. We can compute the change in the energy from system 1 if delta X and delta E are both small. The delta E piece we've discussed. The change in the entropy is how the entropy changes with energy times the amount of energy that changes. That's at fixed mechanical variables. And now there will be a contribution if delta X is small that tells me how the entropy changes with that mechanical variable holding everything else constant. This is true if delta E and delta X are both small. If they're both small, we can neglect the cross term that would go like delta X times delta E, as well as higher order terms that go like delta X squared and delta E squared. Now, how the entropy changes with energy, that's our old friend, the temperature. These are all ones, except for that one. Let's imagine that we prepared the system in such a way that the temperature on the left was equal to the temperature on the right. T1 is equal to T2, which we'll just say is T. Now we need to introduce another definition for how the entropy changes with a mechanical variable. How does the number of microstates change with the volume, or the number of microstates change with the number of particles? Let's define that as minus F over T. So a mechanical variable changes its entropy by a factor of 1 over temperature times some F judiciously chosen because it will act like a corresponding force for that mechanical variable. All right, if in this case T2 is T1 is T, the total delta S is going to be equal to the delta E piece will go away. I'll have a delta X piece minus delta X times over T, F1 minus F2. For a spontaneous change, that needed to be greater than or equal to 0. Again, just noting that we can write the entropy change for both systems in the same way. Reminding ourselves that there's a conservation of X's and E's. So for a spontaneous change, the change in entropy has to be positive. If the temperatures are the same, that means that corresponding change in entropy occurred just due to that term, the repartitioning of mechanical variables. And what we can then deduce is if F1 is greater than F2, so the term in the parentheses is positive, it must be the case for a spontaneous change that delta X is negative. Or in words, X, the mechanical variable, flows or changes from large F to small f. That's a bit abstract. For X being the volume, F is an old friend. It's minus the pressure. And what we've just found is that volume flows from small pressure, from large pressure to small pressure, from volume flows. So if I have a high pressure, the volume will increase. If X is the number of particles, we would say that F is mu, the so-called chemical potential. So matter, mass, number of particles, will flow from high chemical potential to low chemical potential spontaneously. Okay, we'll explore spontaneous changes of mechanical variables, ways of rationalizing these definitions for old friends like pressure and chemical potential in the next couple lectures. And we'll be in a position then to start tackling some more concrete systems and thinking about using this framework to compute things that you might care about. All right, thanks for your attention. I'll see you at the live session later on Thursday.